Good day everyone, my name is Hamdahan Ayasio from Bina Nusantara University, Indonesia, together with my colleague from University of Singapore Bangsa Karawang. I'm pleased to share our collaborative research titled Oncom Fermentation Process Monitoring System using IoT and Firebase. This work was previously presented at an international conference, and through this video, we aim to share key insights from our study to a wider audience. The focus of this research is to integrate modern IoT technologies into the traditional food fermentation process, particularly the production of oncom, one of West Java cultural heritage foods, to improve efficiency, consistency, and safety. This presentation is organized into four main sections: introduction, research methodology, research and discussion, and conclusion. In the introduction, we will describe the background, existing problems, and related studies. The methodology section outlines the system architecture, workflow, and evaluation methods. The research and discussion section presents system implementation, performance testing, and outcomes. Finally, the conclusion summarizes key findings, implications, and potential future developments. Okay, for the background, oncom is a traditional fermented food from West Java, Indonesia, processed manually through national fermentation. Currently, there is no automation in controlling essential environment parameters such as temperature 25 until 30 Celsius and humidity 70 until 90%. Fermentation maturity is determined subjectively by color and aroma, which result in inconsistent quality and higher contamination risks. The main problem identified is the absence of a real-time automated monitoring system capable of maintaining stable fermentation conditions and providing accurate process feedback to producer. Previous research has implemented IoT-based systems in food fermentation such as cacao and rice, focusing mainly on temperature, pH, and alcohol level control. However, none of these studies integrate sensor, cloud database, mobile accessibility, and network performance evaluation into a single platform. Therefore, this research aims to develop an IoT-based monitoring system for oncom fermentation using Raspberry Pi 4B DHT22 sensor, 7-inch HMI, and a Firebase cloud database. The proposed system monitors temperature, humidity, and visual maturity in real time and evaluate its reliability through quality of services analysis. The research followed the waterfall model consisting of 5-stage system analysis, design, implementation, testing, and evaluation. The proposed IoT system integrated sensor hardware, a microcomputer, and a cloud database. The Raspberry Pi 4B acts as the central controller, processing sensor data and displaying information through a human-machine interface. The collected data are stored in the Firebase real-time database and accessed by the Oncom mobile application for remote monitoring. This integration ensures data consistency and accessibility both locally and remotely. The system workflow starts with a camera capturing fermentation image and the HT22 sensor measuring temperature and humidity. The Raspberry Pi 4B process and display this reading on the HMI touchscreen while uploading the data to Firebase. The Oncom mobile application retrieves this information from the cloud, allowing users to observe the fermentation process in real time. This architecture ensures continuous synchronization between physical device and the cloud. providing reliable monitoring from any location. The interaction between user and the system is simple and efficient. User places the Oncom substrate into the fermentation chamber, and the system automatically begins to record temperature, humidity, and maturity level. Data are shown on both the HMI and the mobile interface, allowing users to check the process locally or remotely. Additionally, users can activate the cleaning and control mechanism through the interface, ensuring hygiene and easy system maintenance. To validate the system performance, format evaluation we conduct sensory accuracy testing, compare IoT reading with standard reference instrument to verify measurement precision. Data transmission testing examine the consistency of communication between the Raspberry Pi and Firebase. Network quality of service evaluation analyze parameters such as throughput, packet loss, delay, and jitter to assess network suitability. Lastly, mobile application testing involves both black box and white box approach to confirm software reliability and logical correctness. The hardware implementation consists of several integrated components. The Raspberry Pi 4B serves as the main controller, managing sensor input and controlling actuator through GPIO ports. The HT22 sensor measures temperature and humidity, while the 7-inch HMI display provides local real-time visualization. Data are transmitted via Wi-Fi to the Firebase cloud database, ensuring reliable and continuous data flow for monitoring purposes. The software was developed using Python for handling data acquisition, local visualization, and synchronized with Firebase. On the user side, the mobile interface was designed using Cordula, providing a user-friendly interface that allows login, registration, real-time monitoring, and data download. This integration between hardware and software components guarantees seamless end-to-end communication across device and platform. The system mobile application includes three main modules: login, registration, and monitoring. The login module validates credentials through Firebase authentication. The registration module enables new users to securely create accounts, ensuring data integrity and preventing duplication. The monitoring modules, the next slide. The monitoring modules allows users to observe fermentation progress, view sensor data, and check actuator status in real time. This multi-layer structure provides accessibility and control with strong data protection. Accuracy testing demonstrates reliable sensor performance. The temperature sensor achieves a mean deviation of 0.47 Celsius and an accuracy rate of 93.33%, while the humidity sensor records a mean deviation of 0.55% RH with the same accuracy. This result confirms that both sensors are suitable for real-time monitoring in a fermentation environment where consistency is critical. Data transmission from Raspberry Pi to Firebase was tested in 30 trials and achieved a 100% success rate, indicating stable communication without data loss or duplication. The quality of service evaluation showed that all network providers were capable of supporting real-time IoT data transfer, with provider A delivering the best overall performance in terms of throughput, packet loss, delay, and jitter. The mobile application was tested using both black box and white box methodology. In black box testing, 10 scenarios were evaluated, including login, registration, data visualization, and downloading feature, all of which passed successfully. White box testing used flow graph analysis and cyclomatic complexity to validate internal logic. All independent paths were verified and no unused plans were found, indicating robust and reliable code structure. Overall system performance. The integrated system demonstrates strong performance across all components. The hardware, software, and cloud layer operate in full synchronization, maintaining stable data transmission and real-time updates. The system achieved both high accuracy and excellent reliability, proving its capability for long-term deployment in monitoring Oncom fermentation and potentially other food processing environments. In conclusion, the developed IoT-based Oncom fermentation monitoring system successfully achieved its objective. The temperature and humidity sensor provide more than 90 accuracy, the data transmission remained fully stable, and the network demonstrates excellent QoS performance. The mobile application proved efficient through both functional and structural testing. This research contributes academic novelty by integrating real-time sensor to cloud synchronization, visual interface control, and systematic performance validation. The implication of this research extends beyond Oncom fermentation. Future development will explore AI and machine learning integration for automatic maturity classification and digital twin simulation to optimize fermentation control. The system can also be adopted for other fermented products such as tempeh, tapa, yogurt, and kimchi, and applied to micro, small, medium enterprise to support digital transformation in traditional food industry. Okay, thank you for watching this presentation. We hope that our research demonstrates how IoT and cloud technology can be effectively applied to modernize traditional fermentation practice. We look forward to future collaboration and continued innovation in smart agriculture and digital food technology. For further inquiries or research partnership, please contact our team. And once again, thank you for your attention.